Welcome back to Chapter 15. In this video we're going to finish up the chapter and think about the solar cycle. So the fact that the sun goes through periods of more activity and less activity. We're going to talk about how we know that and what effect that has on the Earth. So in our early chapters, when we were talking about the history of astronomy, we mentioned Galileo and his telescope and the many different things that he looked at and recorded. And one of the things that Galileo recorded even back in the 1600s was observations of sunspots. So not just that they existed, but that from one day to the next, as he recorded them, they actually moved across the surface of the sun in such a way that showed him that it wasn't the sunspots that were actively moving, but rather that the sun itself was rotating. Now what that tells us is that even with the very, very first telescopes, sunspots can be easily visible. And so careful tracking of sunspots has occurred over decades and even centuries. And careful tracking of these allow us to kind of figure out patterns in the data. So, for example, this picture here, what we're looking at is each of these small points is showing where sunspots actually occurred compared to the sun's equator. The sun's equator, like the Earth's equator, is basically the in-between the sun's north and south poles. Now what we notice is that the pattern has this weird shape like a butterfly, hence the name butterfly diagram. And there's a pattern that seems to repeat every 11 years or so. So if we look, for example, at the 1900 mark, at the very start of the 1900s, there was a couple of sunspots at the equator, but then all of a sudden things seemed to reset. And sunspots were far away from the equator, and year by year they tended to migrate towards the equator until the 1912, 1913, it seemed to reset again. If we look a little more closely, what we notice is that those vertical bars that were given for each decade, that's telling how much space is 10 years. This cycle is a little bit longer than that, so it's about 11 years long. The color coding of these dots, by the way, is how many sunspots there were. So if we look in the 1960s and 1950s into 1960, the fact that we see more of these lighter colored yellow points means there were a lot more sunspots in that cycle than there were in the previous ones. If we look at that and try to figure out what could be causing that motion, if we're paying attention to where the sunspots are over time, then what we can actually notice is that the sun does not rotate like a solid object. Every single part of the Earth, in comparison, every single part of the Earth rotates every 24 hours because it's one solid object that is rotating. The sun, however, doesn't act the same way. Because it's a plasma, it doesn't have to act like a single solid object that rotates, and instead the plasma near the equator goes around faster. It takes maybe 27 days to go around, and the plasma near the poles takes actually like 31 days or so to go around. This process is called differential rotation, and it is absolutely key for this solar cycle. So if we imagine the sun's magnetic field, which exists, we just can't see it, but if we have magnetic field lines that normally just go from the South Pole up to the North Pole, kind of vertically. So we can imagine possibly taking a tennis ball and cutting a hole through it so we could string a whole bunch of rubber bands through the middle but then around the outside. If we started to pull those rubber bands around the equator, around the center, and wrap them up, we would basically get more and more wrapping until eventually, with our tennis ball rubber band scenario, if we pull a rubber band too much, it snaps. In the same kind of way, Magnetic fields, if you pull them too much, they'll snap. They'll basically reset and reconnect with each other. But when they reset themselves, they actually flip the poles. And so in this set of images here, we have north at the top, south at the bottom. But after about 11 years worth of wrapping, that's when we kind of get to that extreme where the magnetic fields can't handle it anymore. The field snaps and resets, and then south is on the top and north is on the bottom. So technically the solar cycle is 22 years long to get back to its starting point when you think about the magnetic field. But 11 years is what we actually notice, because if we look at just the number of sunspots, we see that whether we're looking at the top here, which is month by month, there's one single point for how many sunspots there were. The bottom plot has things smoothed out a little bit and on a slightly different scale. But what we see is that we can't tell the difference between a solar cycle where there's north on top and south on the bottom, or a solar cycle where there's south on top, north on the bottom. So 11 years is functionally what that solar cycle acts like. There are some overall trends. So first of all, in this set of images, we can still see that 1950s, 1960s bump where there were slightly more sunspots than the other ones. That's what we saw in the butterfly diagram, so it's still visible here. We can see that sometimes there's just less sunspots overall than others. So in both of these diagrams, we can see that at the start of the 1800s, there were just fewer sunspots for several decades, for several cycles, and that's just kind of natural variation. In the bottom image here, in the 1600s, from like 1650 to 1700, we actually had several decades of time where there were very few, if any, sunspots. This is called the Maunder minimum, and the really important thing to remember is that this means that there was something weird happening with the magnetic field of the sun, but the sun was still producing just as much energy, just as much light, just as much heat as it always was. There was just something weird going on with the magnetic field. Something that we haven't quite figured out, but it didn't affect what amount of sunlight and energy the Earth was receiving during that period. Had no effect. Okay, so we know that there's a solar cycle because of the tracking of sunspots for the most part. But when we talk about the sun being active and inactive, what we really care about is not the sunspots specifically, but the parts of the solar activity that affect the Earth. And that's what we mean when we talk about space weather, and we'll talk about both sections 15.3 and 15.4 together to finish up this video. Okay, so sunspots, if we look at this image on the left, first of all, we see the granulation pattern that we talked about in the previous video that comes from the motion of plasma up in the convection zone and back down again. Sunspots are regions where there's a larger area where that hotter plasma cannot make it up to the surface to be that brighter part of the granulation pattern. That whole area is being prevented from getting that new hotter plasma. The reason that there's that color difference is because of the difference in temperature, where colder means that it's a darker red and colder means that there's less overall energy being produced. It is because of really strong magnetic fields that we have those sunspots basically being limited from having plasma move up, because the magnetic fields are kind of stifling that convective motion. We won't get into the details, but the reason that we know that sunspots have very strong magnetic fields is through a process called the Zeeman effect, which allows us to take a spectrum of that part of the surface, and rather than a single spectral line, we actually get that spectral line split into multiple pieces through complex physics that we won't get into, but the amount of splitting tells us how strong that magnetic field is. The reason I mention it is because we're always in science trying to make sure we understand that there are observations that are informing our facts rather than just making stuff up and hoping that it fits. The observations are always the most important. And so the Zeeman effect is the way that we know sunspots have strong magnetic field. And by looking at different layers of the photosphere and then the chromosphere and the corona, what we learn is that sunspots, which we know have strong magnetic field strengths, are the same places where we see active, lit up parts of the corona and big loops of material following magnetic fields. And so everything kind of connects. Active regions are a key term for us. Active regions show up when we look at images that are showing us the corona, so images in the extreme ultraviolet or X-ray. And sunspots are basically the footpoints of larger loops of material. Now, these larger loops of material might have the names prominences or filaments. Those terms are not as essential to our course, but both of them occur in active regions, and it's basically showing us big loops of material that are slightly less connected to the sun and can be more easily ejected out into the solar system if the magnetic field kind of reorganizes and reconnects. This is why active regions are so important. Their name tells us exactly what they do. They are regions of the corona where the sun is more active. And so these prominences, shown here, can become extremely, extremely large. So the left here is showing an approximate size of the Earth compared to one of these big loops of material that are making those loops because that's what the magnetic field looks like. We can't see the magnetic field, but we can see its effect. And so strong magnetic field is found where sunspots are seen in the photosphere, and strong magnetic field is found where we see active regions in the corona, because they're basically just different heights of the same overall process. It's in these active regions where we can have flares and coronal mass ejections. Now, flares are bright light, they're basically a bright flash of light. And so when we talk about flares, what we're talking about is extremely high energy photons. Those flares can send those extremely high energy photons in any direction, sometimes towards the Earth, and then we actually can measure those X-ray photons with satellites that we have above Earth's atmosphere. The flares themselves don't do a lot of damage to us here on the ground because they are just high energy photons that our atmosphere is already very good at blocking. But coronal mass ejections can have a very strong effect. So coronal mass ejections, from the name, they're coming from the corona. They contain a lot of mass or material, and ejections mean they actually leave the sun and are flung out into space. So flares, it's just light, photons, but coronal mass ejections, or CMEs, that's physical material. That's protons and electrons and physical plasma that is being sent off into space. And that's what's shown here on the far right of the picture here. So this is an example set of images from a coronal mass ejection. In A, we have a picture of the photosphere, and we see some sunspot groups which show us where we should be seeing active regions in other images. In B, we're looking at the sun again, this time in X-rays, and we see that the places where we see sunspots tend to be the same places where we have a lot of activity in the X-ray image. And if you see those long kind of extended lines in that middle bottom active region, that's actually places where the image got so saturated by those high energy photons from the flare that it kind of saturated that part of the image. Parts C and D are using the coronagraph that we mentioned in the earlier video to block out the disk of the sun. We're now looking further away, and we can see this big loop of material, CME, a coronal mass ejection, that in part C is kind of close to the sun but being sent out, and in part D is even farther from the sun and being sent out. There's a video of a different event from 2012, which has a lot of different pieces to it, and we'll have that link for you to look at on Blackboard as well. So space weather, in summary, comes from three main sources. The solar wind, which we mentioned in the previous video, which the fastest parts of the solar wind come from coronal holes, which are regions where the magnetic field's kind of open to the solar system and not in big loops. And so solar wind is from a very different part of the sun outer layers than the other two. Coronal mass ejections are sort of short-term bursts of physical material that's sent away from the sun. And solar flares are short-term bursts of just light particles, photons, that occur in active regions as well. The solar wind is kind of a constant outflow away from the sun, but if we get a really fast gust, basically, a fast amount of this solar wind as a coronal hole might like swing into view, then that can actually buffet against our magnetic field on Earth, and a changing magnetic field can create electric current. Now, let's think a little bit more about the effect of these three categories on the Earth itself. So the first is particles from the solar wind, or CMEs, or some of the particles that come along when we have just a flare but not a bigger CME. Those are trapped by the Earth's magnetic field. If it's a charged particle, it will kind of follow the field lines until those field lines connect back into our atmosphere, and that comes down to the north and south poles. A lot of people just think about the northern lights, and that is what's pictured here, but overall this is aurora. And so in the northern hemisphere where we are, these northern lights, the image here is showing an example of that. That's what we're familiar with, but the southern hemisphere has the southern lights. So we have aurora borealis, they have aurora australis, but the same idea. And in both of these cases, what we're seeing is electrons that were following the magnetic fields, the electrons from space, from the sun, come down and strike an air molecule. And in a bit of complex physics, but at its heart, very similar to what we talked about in Chapter 5, if we have something that is in an excited state, it wants to be in a neutral ground state. And in order to drop back down into that neutral ground state, we have to give off energy. And that's what's happening. Those molecules are giving off photons. They're giving off light as they go from being their excited state back down to their neutral state. And that's what's happening in an aurora. But space weather is not just aurora. It's not just the northern lights, the sort of pretty pictures that we might see from northern latitudes. Space weather can affect the Earth quite considerably. And so to think about these effects, we're going to use a specific event from history from 1859 called the Carrington event. It's named this because Richard Carrington was the only one to initially see the activity on the sun that kicked off this whole process. He was taking observations of the sun because he was an amateur astronomer, and this was something he did kind of every day. He's one of the many people who contributed to our overall sunspot record. The fact that we have the number of sunspots from back in the 1600s is because there were always enough astronomers who were taking this data every day. And he took the following observation on the left. And we see this A, B, C, D that he's drawn here. And what he's indicating is he actually, when observing the sun, saw bright flashes of visible light at those sunspots. Now, sunspots are usually extremely, extremely high energy photons, so usually just ultraviolet or X-rays. But this flare, sorry, I said sunspots, I meant flare. This flare, or set of flares, was actually so much energy that the energy distribution got wider and included visible light photons as well. So he saw those, and since those photons were moving at the speed of light, he saw them about 8.5 minutes after they were produced, and didn't think too much of it. However, in the following several days, there were a whole lot of things that happened. People could see the northern lights, the aurora, at much, much lower latitudes than had ever been seen before. And remember, this is the 1800s. Telegraph lines were the way that people communicated with each other, long lines of metal. Those telegraph lines were overloaded and stopped working on a sort of almost global kind of scale. And in a couple of places, the electricity running through the lines was so high that it started electrical fires in some of the telegraph stations. Okay, so what happened? The flare that Carrington saw was in an active region where, at the same time that flare was produced, a huge coronal mass ejection was created, and it was aimed straight at Earth. Now, that coronal mass ejection, when it came to Earth, it has its own magnetic field, and it interacted with the Earth's magnetic field and basically peeled back layers of the Earth's magnetic field, which is why there were particles that were at much lower latitudes than normal. So we're basically peeling back the layers so that you're getting closer and closer towards the equator with where those remaining magnetic field lines connect down into the atmosphere. And because we had drastic changes to the Earth's magnetic field, a changing magnetic field creates electric current, and that's one of the sort of big fundamental pieces of physics. We don't need to go into the details of the physics behind that, but if we take as fact that changing magnetic fields create electric fields, then what that means is all of a sudden, because of these global changes to the Earth's magnetic field, we create current in any long pieces of wire, which in the 1800s was pretty much just the telegraphs. And even the following week, there was so much residual electricity that they kind of ran on their own without being connected to the grid, quote unquote. But if that same kind of event happened now, in the 21st century, all of our power lines are long pieces of metal, and so our power grid could be taken out. And if we aren't aware that it's going to happen, in the same way that we had electrical fires at telegraph stations, we could have major problems with transformers, including breaking them in a way that is not fixable. And because we don't have big warehouses of non-used transformers just ready to go to be replaced, we could be out of power. We could be in blackout conditions for months or even years as we try to build the new missing pieces of our power grid. Oil pipelines are long metal tubes, and space weather can actually erode oil pipelines as electric current runs through that metal when it's not supposed to. And so an event of this size is not common, but it is the case that it's always a possibility, and we're not actually yet at the scientific understanding to be able to see the sun and predict exactly when it will make a flare or send off a CME. However, we do have a dedicated group of scientists at the Space Weather Prediction Center in the same part of our government structure as the Weather Channel, that once we see a flare or a CME, we can track them very well, and within a couple of hours know exactly when they're going to start affecting Earth's magnetic field and if they will be affecting Earth's magnetic field. The reason this matters is because if we don't have a forewarning, a lot of problems could happen. So first of all, we talked about the power grid. We talked about oil pipelines. I didn't mention that these CMEs and large-scale changes would be affecting sort of our lower satellites. And so GPS could be lost, which means we would have to ground all air traffic because planes rely on GPS to get where they're going. And it would be extremely widespread problems. If we know that this thing is coming, in the same kind of way that if there's a thunder lightning storm, you've been taught to kind of unplug key things, or in general you might have key things like computers or TVs through a surge protector. That kind of idea, but in a big lightning storm we might even unplug stuff from the wall. That same kind of thing, if we had the forewarning, we could kind of plan ahead, let it blow past, affect things, but if we have basically taken the transformers off the grid and we've had all the planes land, then there won't be as many long-term or long-lasting consequences of an event like that. So it's something that is rare and unlikely to happen. There were a lot of circumstances that kind of all had to line up. Because remember, any CME, no matter how big or small, it can go off in any direction from the sun, and there's a lot of directions that aren't towards Earth. And we only have to worry about the direction that is towards Earth. It's a very small part of the overall volume that the CME could be sent off in. And the Carrington event, the magnetic fields of the CME were exactly opposite the Earth, which allowed that sort of peeling back process to be extremely, extremely effective. And that was also something that is unlikely to happen in that same way in the future. So this video has given us a lot to think about on the specific way in which the sun affects the Earth. In our next videos for this week, we're going to be turning to chapter 16, where we kind of take a step back from the sun as being a thing that directly affects us and that we can take detailed observations of, and treat it more like an example star, and think about how we can learn more about the sun and use that to inform our understanding of other stars. So that's all I have for you in this video, and hopefully we don't come away too scared of our sun. It still does a whole lot of good for us, and space weather is something that we are aware of and can easily kind of prepare for if something were to be headed our way. I will see you in the next video.